This time let's look at the titration curve for the titration of a weak base with a strong acid. So let's say we're starting with 40 milliliters of a 0.1 molar solution of ammonia, and to our ammonia we're going to add a strong acid. We're going to add some HCl. In part A, they want us to find the pH before we've added any acid. So we have ammonia present. So let's go ahead and write NH3 right here. We have a solution of ammonia. So we write water here. Since ammonia is a base, ammonia is going to take a proton from H2O. And if you add an H plus to NH3, you get NH4 plus. So we're going to make some ammonium here. And if you take away an H plus from H2O, you get OH minus, or hydroxide. Our initial concentration of ammonia is 0.1 molar. So right here we write initial concentration of ammonia, and that's 0.1 molar. And this is a weak base equilibrium problem, right? So we're going to assume an initial concentration of 0 for our products here. Next, we think about the change. So we're going to lose a concentration of ammonia. So a certain concentration of ammonia is going to react, and we call that concentration X. And since that concentration of ammonia, NH3 turns into NH4 plus, whatever we lose for ammonia, we gain for ammonium, right? So we write a plus X over here. So we're going to gain a concentration of ammonium, and we would gain the same concentration of hydroxide. So at equilibrium, right, our concentration of ammonia is going to be 0.1 minus X. For ammonium, it would be X, and for hydroxide, it would also be X. Next, let's write our equilibrium expression. Since this is a base, we would write Kb, and we have the concentration of products over reactants, right? So for our products, we would have the concentration of ammonium, so that's X, times the concentration of hydroxide, which is also X, over the concentration of ammonia, which is 0.1 minus X. So make sure you've seen the video on weak base equilibrium before watching this one here. All right, next, we know that the Kb for ammonia, let's say they gave it to us, and it's 1.8 times 10 to the negative 5. So that's equal to X times X, which is X squared, right, over 0.1 minus X. But here's where we assume that this concentration is really small compared to 0.1. And therefore, 0.1 minus X is approximately the same as 0.1. And this just makes the math a lot easier. So now we have to solve for X. So let's get a little bit more room here and take out the calculator. We have 1.8 times 10 to the negative 5. We need to multiply that by 0.1 and then take the square root of that. So we take the square root of our answer and we get X is equal to 0.0013. So X is equal to 0.0013. And if we go back up here, we can see that X represents the concentration of hydroxide ions at equilibrium. So let me go ahead and write that here. This is equal to the concentration of hydroxide ions. That's 0.0013 molar. If we have the concentration of hydroxide ions, we can find the POH, because the POH is equal to the negative log of the concentration of hydroxide. So the POH is equal to the negative log of 0.0013. And let's get out the calculator and do that. Negative log of 0.0013 is equal to 2.89. So the POH is equal to 2.89. And our question wanted us to find the pH. So remember, pH plus the POH is equal to 14. So I can take the POH and plug it into here and solve for the pH. The pH would be equal to 14 minus 2.89, which is equal to 11.11. So we found our pH before we add any of our acid. It's 11.11. So on the titration curve, right, I can see down here, this would be 0.0 milliliters of our acid added, and that's where we are. And the pH should be 11.11, so somewhere right about here, right? So I'm saying that's a pH of 11.11. For part B of our question, what is the pH after the addition of 20 milliliters of our 0.1 molar solution of HCl? So the concentration of HCl is equal to 0.1 molar. And we know molarity is moles over liters. So that's moles over liters. We're adding 20 milliliters. So if you take 20 milliliters and move your decimal place 1, 2, 3, that's 0.02 liters. So we're adding 0.02 liters here. And so we solve for moles. 0.1 times 0.02 is equal to 0.002. So that's how many moles of HCl we are adding. So HCl, you can think about this as H plus and Cl minus, or if you think about adding your proton to water, H plus and H2O give you H3O plus. So you could consider this to be the number of moles of H3O plus that we're adding. Next, what's the concentration of ammonia that we started with? So the concentration is 0.1 molar, so the concentration of ammonia is equal to 0.1 molar, right? And we want to find moles of ammonia. What's the volume of ammonia? Well, 40 milliliters would be 0.04 liters. So we have 0.04 liters here. And we solve for moles. So that's 0.1 times 0.04. And 0.1 times 0.04 is equal to 0.004. So that's how many moles of ammonia that we have. All right, next, let's think about what happens to the ammonia when we add the HCl. Right, so the acid that's present is going to react with the base that's present. So let's go ahead and write what would happen. The ammonia, NH3, is going to react with the H3O plus that is present. So this reaction goes to completion here. And let's think about what would happen. This is a base and this is an acid. So we're going to protonate NH3 to form NH4 plus. So we add a proton onto NH3 to form NH4 plus. And we take a proton away from H3O plus, so we get H2O. So we have H2O over here. All right, next, let's look at what we're starting with. So this is our neutralization reaction. So let me go ahead and write that. This is the neutralization reaction. We're adding 0.002 moles of our acid here, 0.002. So let's put that right here. So we're adding 0.002 moles of acid. And we're starting with 0.004 moles of our base. So 0.004 moles of our base. So all of our acid's going to react, right? We're going to lose all of the acid that we added. It all reacts, so we're left with nothing here. We're going to lose the same concentration of our base. Right, so the acid is going to react with that much of our base. So we're going to lose 0.002 moles of base. So we're left with 0.004 minus 0.002, which is equal to 0.002. So half of the base has reacted with the acid and half of the base is left over. So this is how many moles of ammonia we have left over after the acid has reacted. All right, if we're losing this many moles of ammonia, right, since our ammonia turns into NH4+, if we started with 0 for NH4+, that's how much of ammonium we are gaining here. So we're gaining 0.002 moles of NH4+. And so we're going to end up with 0.002 moles of ammonium, NH4+. All right, so we have moles of ammonia and we have moles of ammonium. And next, we need to think about the concentration of ammonia and ammonium that's present. All right, so if we're thinking about concentration, we need to know volume. So let's go back up to here and let's see what the total volume is now. We started off with 40 milliliters of our ammonia, and we've added 20 milliliters of our acid. So 40 milliliters is what we started with. We added 20 milliliters, so our total volume is now 60 milliliters, or 0.06 liters. Right, so this is 60 milliliters. We move our decimal place 1, 2, 3, and that's 0.06 liters. So now we have liters and we have moles. So let's find the concentration. All right, so let's start with the concentration of ammonia. So the concentration of ammonia is equal to moles over liters. We have 0.002 moles of ammonia, so 0.002 moles of ammonia. We divide that by our volume, right? Our total volume is now 60 milliliters, or 0.06 liters, and so we can find our concentration. Right, so we could go ahead and do that here. 0.002 divided by 0.06 is equal to 0.0333. Right, so we get this is equal to 0.0333. This is a concentration, so this is molar. Next, we do the same thing for ammonium. Right, so what's the concentration of ammonium here? Well, we had the same number of moles, right? That's 0.002 moles of ammonium, and the volume's the same, 0.06 liters, and so therefore it's the same calculation. We get the same concentration of ammonium ions in solution, 0.0333 molar. So now we have equal concentrations of a conjugate acid-base pair, right? NH4 plus and NH3 is a conjugate acid-base pair. So we have a buffer solution, right? So now we have a buffer solution. So our goal was to find the pH, and since we have a buffer solution, the easiest way to do that is to use the Henderson-Hasselbalch equation, right? So we go ahead and write out the Henderson-Hasselbalch equation, which is the pH is equal to the pKa plus the log of the concentration of A minus, the conjugate base, over HA. All right, so let's think about what the pK is. How can we find the pKa? Well, we know the Kb for ammonia, right? We know the Kb for ammonia, and we know that Ka times Kb is equal to 1.0 times 10 to the negative 14. All right, so if we plug in the Kb, 1.8 times 10 to the negative 5, all right, this is equal to 1.0 times 10 to the negative 14. We can solve for the Ka. And to save time, I won't show this on the calculator. I'll just go ahead and write the Ka is equal to 5.6 times 10 to the negative 10. So if you remember this from an earlier video, if you multiply for a conjugate acid-base pair, if you multiply Ka times Kb, you get this. And so now we've just solved for the Ka is 5.6 times 10 to the negative 10. This is for NH4 plus. So next we can find the pKa, because the pKa is the negative log of the Ka. So the negative log of 5.6 times 10 to the negative 10. So let's get out the calculator and do that. Negative log of 5.6 times 10 to the negative 10 gives us a pKa of 9.25. So the pKa is equal to 9.25. So we plug that in to our Henderson-Hasselbalch equation. So now we have the pH is equal to 9.25 plus the log of the concentration of A minus. A minus is your conjugate base, right? So that's what we're talking about up here for ammonia. So that's 0.0333. So this is equal to 0.0333, and that's over the concentration of your acid, which is NH4 plus, which is also equal to 0.0333. So that's equal to 0.0333. All right, so this is on the right, all of this is equal to the log of 1. And the log of 1 is equal to 0. Right? Log of 1 is equal to 0. So therefore, your pH is equal to your pKa, which is equal to 9.25. So the pH is equal to 9.25, since all of this is equal to 0. So now we can find our point on our titration curve. All right, we've added 20 milliliters of base. Let's go of acid, I should say. Let's go back up here and look at our titration curve. All right, we've added 20 milliliters of our acid. So right down here, 20 milliliters of our acid. So let's find this point on our titration curve. So we're right there. And we calculate the pH should be 9.25. So if I go over here, the pH should be equal to 9.25. So we're still before the equivalence point.